We know that conductors are characterized by a large number of free charge carriers which move between the atoms of the conductors and also within the volume of the conductors. Metallic conductors have a large number of free electrons. When a metal conductor is placed in an external uniform electric field of strength, say E, we know that charge distribution takes place in the conductor due to the movement of the free charges, and the electrostatic induction occurs in such a way that in equilibrium, the electric field strength E' inside the conductor due to the induced charges is equal and opposite to the external field of strength E. Hence, the net electric field inside the conductor is zero, and the conductor is said to be in electrostatic equilibrium. Unlike conductors, dielectrics like rubber are those materials in which there are either practically no free charge carriers or free charges. Dielectrics are electrically non-conducting materials. A dielectric material can be made of either polar molecules or non-polar molecules. Polar molecules are those in which there always exists a separation between the average positions of the negative and positive charges in the molecule, irrespective of whether it is in an external electric field or not. Such a molecule is called a permanent dipole and will possess a permanent dipole moment. Water molecule is one such example of a polar molecule. In a water molecule, the center of the negative charge is at the oxygen ion, since it is the negatively charged ion, and the center of the positive charge is at the midpoint of the line joining the two positively charged hydrogen ions. These average positions of the positive and negative charges act as point charges, and hence the polar molecule behaves as a permanent electric dipole. As such, we can say that all polar molecules like water, hydrogen chloride, etc. behave as permanent electric dipoles. Therefore, even in the absence of an external electric field, such molecules possess a permanent electric dipole moment. Non-polar molecules are those which do not possess a permanent dipole moment like the polar molecules. Hydrogen and carbon dioxide molecules are examples of such non-polar molecules. In such molecules, the average centers of the positive and negative charges coincide. Hence, they do not possess an electric dipole moment in the absence of external electric field. Now let us see what happens when a dielectric with non-polar molecules is placed in an external uniform electric field of strength E. Due to this uniform external electric field, the positive charges in the molecules are displaced in the direction of the electric field, and the negative charges in them are displaced in the opposite direction of the electric field. Therefore, in the dielectric with non-polar molecules, the molecules now possess some induced electric dipole moment, and it is said to be polarized due to the external electric field. Now let us consider the case when the dielectric material is made of polar molecules. In the absence of the external electric field E, the polar molecules in the dielectric are such that their electric dipole moments are randomly oriented due to thermal agitation, and hence the total dipole moment is zero. Now when they are placed in the uniform electric field of strength E, we know that every dipole in it experiences a torque, which rotates the dipoles in such a way that they align in the direction of the electric field. Thus, the dielectric material with the polar molecules is said to be polarized. The degree of alignment of the dipoles with the external electric field direction depends on the temperature and also on the external electric field strength. In general, the alignment increases with increasing electric field strength and also with decreasing temperature. Thus, we observe that the dielectric material is polarized irrespective of whether it is made of polar or non-polar molecules, and they develop a net electric dipole moment in the presence of an external electric field. Linear isotropic dielectrics are those in which the induced dipole moment is in the direction of the external electric field and is proportional to the external electric field strength. Now, when this linear isotropic dielectric is placed in a uniform electric field of strength E, it gets polarized. Let us consider the polarization P of such materials, which is defined as the electric dipole moment per unit volume. For linear isotropic dielectric materials in a uniform external electric field, the polarization P is equal to psi E into E, where psi E is the electric susceptibility of the material. Now, each small volume element of the linear isotropic dielectric having a volume dV has a net polarization equal to P dV due to all the dipoles in it in the direction of uniform electric field. Here, it is important to note that the net charge in each volume element will be zero. The resultant effect in the material due to the uniform external electric field will be the formation of an induced positive charge density plus sigma induced on the right face of the dielectric and minus sigma induced on the left side of the dielectric. This in turn causes a weak electric field of strength E' to be induced in a direction opposite to that of the uniform electric field of strength E. Therefore, the net electric field E0 in the dielectric will be equal to E minus E'. Thus we observe that the polarization effect causes a decrease in the net electric field within the dielectric. Dielectric materials, being non-conducting, are useful in many devices like capacitors, transformers, etc. because of their inherent properties.